Thank you, everyone, and thank you to the organizers for this invitation to be here today. It's truly an honor over the next 20 minutes or so to discuss the Quantum Information Science program at the U.S. Air Force Research Laboratory. A little bit about Air Force Research Laboratory in general. I'm sure folks aren't too familiar about it. We'll go into some detail as to where we're actually located, but we have a very large workforce of about 6,000 military, government, and civilian, with another 5,000 or so on-site contractors. We're located in 10 different states, 3 international locations, actually just recently moved up to 5 or so, with quite a bit of investment in terms of our core R&D funding as well as external funding. Here's a quick snapshot of our locations throughout the United States. I already mentioned the 10 different geographic locations. I'm actually located in Rome, New York, in upstate New York, at the Information Directorate, where I am the Deputy Director. I'm also responsible for coordinating the quantum program across the entirety of AFRL, which we'll get into detail as we go throughout our talk. You can see some of our other major locations, such as in New Mexico, where we have the Space Vehicles and Directed Energy Directorate, Ohio at Wright-Patterson Air Force Base, where we're headquartered, as well as Human Performance, Aerospace System, Sensors Directorate, and Materials and Manufacturing. And then finally, would like to highlight our Air Force Office of Scientific Research, or AFOSR, headquartered in Arlington, Virginia, but as you see there, 5 different geographic locations or offices located throughout the world, including London, which is the European headquarters. And I will go into some detail as I go through the talk, specifically related to funded work at AFOSR that is now turned into actually startups. So going through our program, here is what we call our operational view of our quantum program at the Air Force. So keep in mind, the Air Force includes not only an air component, but a space component as well, with the stand-up of the U.S. Space Force. So looking at this diagram, you'll see this highlighted throughout my talk specifically as we look at this chart up here. Timing and sensing are grouped together, and then networking and computing are grouped together on the other side, with supply chain as well as workforce development forming the interlocking capabilities. In terms of capabilities, you'll see the color codes here. First off, for timing and sensing, being able to navigate and know where you precisely are in GPS or GNSS denied and degraded environments, as well as for bunker and tunnel detection with advanced sensors, are technologies that we are researching. On the networking side, certainly low probability intercept of communications is of high interest to us. We're really looking to move beyond QKD, and entanglement distribution is our key area of focus there, and we'll go into much detail on that. And then certainly, what else can we do with networks? We certainly see being able to link together quantum computing nodes, been subject to much discussion. And then finally, how we can link clocks together is something that we see as a key application area as well. On the computing side, and again, I'll go into great detail on this, certainly for us, being able to process large amounts of data is very much of interest in areas such as optimization, machine learning, and certainly quantum simulation. Let's see, so let me do this through the build, jump right to it. So again, looking at this chart, kind of breaking it out, both in terms of a time frame, as well as capability delivery. So in terms of self-sustained PNT, we certainly see timing as being available not only here and now with atomic clocks, but certainly sensing in the 2 to 5 years time range to give us capabilities in PNT. On the distributed computing side, being able to link together those quantum computers of interest where you're going to require more entanglement. We see networking kind of being further out, maybe 5 to 10 years. And then certainly computing, if you're looking to develop a full-fledged fault-tolerant quantum computer, certainly 10 plus years out as well. Moving into our geographic locations and kind of breaking this down, I think this is a really great chart to show the breadth of our capabilities across the enterprise. So certainly down in New Mexico, down here, our capabilities for in directed energy as well as space vehicles directorates. There we're working on the PNT functions in terms of both clocks and quantum sensing. as well as quantum networking for our satellite-based capabilities, which I'll go into. At the Information Directorate, where I work, quantum networking from ground to air is very much of interest to us, as well as air to air, as well as developing quantum computing algorithms and looking at the problem spaces of interest as well. And certainly at our headquarters at Wright-Patterson Air Force Base, in the Sensors Director and the Materials Directorate, obviously being able to develop better devices, higher performance devices, as well as looking at some of the materials and supply chain issues as well. Let's see, moving on to our timing piece. This is a great summary of kind of where we're at now and where we want to move towards. So currently stability on the order of nanoseconds per day under static conditions. You can think of the chip scale atomic clock that has had a lot of funding go into it, been a great success. Our hope is to move past that in terms of stability while maintaining swap as well. So you can see certainly something that we're moving towards there. And in terms of stability, fewer timing updates. Certainly mobile clocks that are able to hold time for weeks to a month on end, requiring fewer updates as well. Obviously, through organizations like NIST, which lead the development of standards for optical quantum clocks, we want to get there, but be able to move the size, weight, and power down, of course, as we move towards platforms for both air and space. On the recent results side, you'll see some what we call our ORAFs, laboratory performance, which stands for Optical Rubidium Optical Frequency Standard, and some of the clock performance that have been developed in-house. And we've also been able to, and this is this bottom piece goes throughout the slides as well in the different areas, a Quantum Collider event that we held in 2020, which was small business funding that the Air Force provided on the order of a total of $40 million spread out across these four main areas that we'll be highlighting here. Really pushing how we can go from the lab out into real capability. And again, it's been a huge success for us. This program started in 2020. Phase 2 is just winding down now, and it's really paid high dividends for us. Now, moving into the sensing piece, very closely tied into timing, of course, as we move towards GPS precision and GPS denied environments. And here we're really looking at how we can shrink sensing capabilities down onto air platforms. And for example, we're currently at GPS accuracy for much less than 1 hour. We obviously need to move that up to much higher standards. We've moved towards actually taking some of our technology that we've developed in-house, and by in-house capability development, I mean things like inertial sensors, gravimeters, gradiometers, and magnetometers, and then moved them towards a shipboard platform as kind of a trial run, if you will. This occurred in a 2022 demonstration with some of our international partners. And this was really looking at how we can move technologies from the lab out into the field, and it allowed us to learn a great deal of continued development that we need, and we'll take this out into further both air and sea tests out in the future with our partners based on what we learned as well. You can see it's a little hard to read there, but some of our recent results that have come from the sensor development, and again, our quantum collider work that was done under our phase 1 and phase 2 STTR. And STTR stands for Small Business Technology Transfer Awards, where a university is partnered with a small business for both a phase 1, which is on the order of about $150,000 US dollars, and then phase 2 was on the order of $1.5 million. Moving on to computing, where I'm going to spend a significant amount of time on both computing as well as our networking portion of our work. So quantum computing, I mentioned earlier that we're really focused in on algorithm development at the Air Force. We are not developing hardware. We really leave that up to the commercial partners that are out there. For example, we have been partnered with IBM since 2019 as a hub on their quantum network, as well as we recently signed an agreement with INQ to partner with them on their cloud network as well. So great partners, both of us, and it's also allowed us to bring in other users into that network for us as we really push forward on algorithm development. Where are we going with the algorithm development? Really focused in on three main things: optimization, which you could certainly imagine the Air Force would be interested in for logistics type problems, quantum simulation, being able to develop new types of materials, as well as other aspects that could lead into new devices and ultimately into actual systems for us. And then finally, machine learning, how we can accelerate the development of machine learning using quantum computing. See some results there in terms of our publications. Really, right now, where we're very interested in is certainly benchmarking the devices we're on. As I mentioned, we're on the IBM, which is a superconductor-based system, and IonQ, trapped ion system. Looking to expand that in the future, but it's been great for our researchers as well as our partners to get access to those systems to really be able to further push the technology development. In terms of application areas, so I mentioned the ones of interest to the Air Force, but as we hear throughout this conference, a wide variety of applications there that will certainly come along as we go through this. Being a hub has allowed us to really build a really smart ecosystem, if you will. We're currently at about 15 partners that work with us on that hub, focused in on problems of interest to both parties. So, for example, we work with industry, we work with academia, we work with small businesses, really focused in, though, on problems that the Air Force will ultimately need to operationalize. What I'd like to do now is spend a couple minutes on investments through the European ecosystem that have been paying large dividends for us. So for the first example would be quantum photonics at Oxford, which is spun out into Orca Computing. And on both these slides, this one as well as the next one, which highlights PsiQuantum, is you really see the long-term investment required from basic research on up to developing an actual product and a spin-off and a startup. So beginning in about 2009 or so, AFOSR, Air Force Office of Scientific Research, awarded grants to Oxford University and Professor Walmsley during his time there. You see multiple grants were awarded, and you can kind of see the step through and progression here and some of the key papers that were published, ultimately leading to a paper on boson sampling on a photonic chip that then really, I think, broke ground onto the development and spin-off of Orca Computing in 2019. And you can kind of see the acronym there for Orca, which stands for Off-Residence Cascaded Absorption Memory. Real key development and quantum computing platform that I think could certainly pay high dividends moving forward. 2022, Orca signed a deal with the UK Ministry of Defence to provide a quantum computer for them. AFOSR is continuing to fund Orca as this technology continues to mature and further develop. And we're also in the Information Director currently looking at a partnership agreement with Orca as well. Moving on to the University of Bristol and a spin-off that ultimately resulted in PsiQuantum, which I'm sure folks are very familiar with as well. So a spin-out of Professor Jeremy O'Brien's group when he was at Bristol University. Grant started in 2012. So again, you see, over a 10-year span here from really basic research on up to commercialization. In the interest of time, I won't go through all the work that's been there, but you will see again, a photonic approach, different approach than Orca is doing, but again, we certainly see this as a very high payoff, upon further development. Two recent results from PsiQuantum that I think this work has really led to. So certainly, being awarded a DARPA program for utility scale quantum computing. That announcement just came out, where PsiQuantum was one of the few partners that were awarded, or collaborators that were awarded those grants. And then Senator Schumer from New York, he announced a $25 million award to global founders in PsiQuantum, which we're running out of the Information Directorate, to really look at fabrication techniques to be able to push this technology further forward. All right, moving on to networking, where I spend pretty much the rest of my time. Early on, I talked about the two pieces of our quantum networking program. First, there's the ground to satellite piece of it, and that's what I'll highlight first. Here, this is work being done at the Directed Energy Directorate down in New Mexico. And as it says, working on technology to be able to develop entanglement between the ground stations and the satellite link. Key to this, of course, would be entangled photon sources. And what we're very proud of is that we've been moving forward with a new agreement in terms of being able to work with the Canadian government on satellite technology between AFRL in New Mexico, the Information Directorate as well, and a satellite launch on the KeySat system, which will be occurring down the line in a year or so. Where that'll take us certainly is, as I talked about earlier, moving beyond QKD and really looking at entanglement distribution. The team has done some great work in the past few years on what was mentioned in an earlier talk, certainly the saturation problem that you get both from daylight and sun. So being able to do some spectral filtering techniques is something unique that the team in New Mexico really brings to the table as well. You'll see also on the left side here are some recent results, right side I should say, on two-way time transfer that the test bed achieved just recently in December 2020. Also key to this, and again, no stranger to the entire talk, but the Quantum Collider event and some of the technology that has been pushed out of that as well. Now we tie that together with our ground and air-based quantum networks, the work being done in Rome, New York. Very similar type of techniques though in terms of really looking at entanglement distribution. In Rome, we're looking at 3 different qubit technologies that you'll see listed up there. Trapped ions, superconducting, and integrated photonics. Each of those brings strength to a heterogeneous type of network. And what we're really focused in on is not only developing those technologies, but the transduction between those sources as well. Multi-node networks are very much key interest to us. We're really working towards a 3-node network where we'll be able to demonstrate the entanglement. We had some great demonstrations this past summer with Qubitech, again from the Quantum Collider event, where they're able to develop some drone to ground distribution technology, quantum technology. We're looking to really push that in our in-house development as well. It's one of the goals of the team in the coming years as well, especially moving towards the following year. And again, the recent results are highlighted there. So being able to develop in-house capabilities in all these areas is something the team is very proud of. We've been partnered with AIM Photonics, which is one of the Department of Defense's manufacturing institutes located in upstate New York. Really been able to move from large 4x8 optical tables into integrated photonic circuits. Key to all this technology, especially as we look to interface that with our superconducting nodes as well. And then finally, our trapped ion work. We started out trapping ytterbium. We've recently moved to barium and have had great success there as well. As we put this all together, this is kind of the key slide here, and this is our distributed networking testbed. We have our Innovari Advancement Center, which I'll highlight on the next slide. But there we're working with our partners on developing technologies, the interface of those technologies. As we look towards operationalizing the technologies, moving more towards Air Force applications and U.S. Space Force applications, here we move them towards our in-house test beds. We just stood up new laboratories for the heterogeneous networking efforts there as well. And then finally, our test sites. I mentioned our interest in drone technology, as well as certainly Starfire optical range in New Mexico. So these really unique off-site capabilities allow us to take that technology and more rapidly move it out into the field and ultimately transition our technology. So we see a really good ecosystem and a progression of development. And I believe this will be my last chart, so let me just spend a minute or so on this. So I think a lot of you have heard about this or are familiar with it, hopefully. This is what we call our Innovari Advancement Center. This is our open innovation and collaborative environment located just outside the perimeter of the AFRL Information Directorate. This is a partnership between AFRL, New York State, as well as the county that we sit in, Oneida County. Oneida County provided the building. They renovated the building to the tune of about $14 million in 2020. What that's allowed us to do is establish in-house laboratories and then really drive at problems hard, deep tech problems. So for example, not just quantum, but other areas we're working on would include AI, machine learning, cyber, as well as drone technologies. The entire building encapsulates 150,000 square feet. The ground floor, which I'll just highlight briefly here, 2 leading edge quantum labs. state-of-the-art labs, each 1,500 square feet, where we invite our international partners in to work with us collaboratively and side by side with our scientists and engineers, really going at those hard problems. And then lastly, co-located with this, you can see it if you could just extrapolate out. There's a hangar there, which was used when this was part of Griffiths Air Force Base for B-52 testing. The hangar has now been converted into a very large drone testing capability, indoor capability, as well as doors open up to a netted feature that allows both indoor and outdoor testing. Given our climate in upstate New York, certainly having the indoor capabilities is key for us through the long winter months. But again, that allows us to bring together all those different technologies and ultimately accelerate the development and getting product out to the field. So with that, I'll end. Thank you very much.
Perfect timing by Michael. Time for one question. Any question from the audience? If not, I have one just to ask Michael.
Sure.
A couple of your slides mentioned you guys have worked pretty openly with the international research community. Is there maybe a front door for people to get in touch with you? And also, I think in the end of June, you have a conference.
Yeah, thanks for that plug. I should have put it on the slide, but we do have what's called Q4I, Quantum for International workshop that we host every year in Rome, New York at the Innovare Advancement Center, bringing together researchers from across the world, industry, academia, as well as small businesses. 3-day workshop. You can go to the website, innovare.org, so you can see the spelling there, INNOVARE.org. Q4I tab will come up, get more information on the agenda and how to register for it. And yes, international partnerships, open door policy, in terms of meeting and aligning with our researchers. You can see me. I'm here this week. You can also go to the Innovare website and connect with us that way as well.